Hello everyone, my name is Harnit Saini. I am assistant professor in Ajay Kumar Garg Engineering College. In the previous video, we were studying about the virtual memory and we were studying about the pages, frames, physical memory, virtual memory, and how the pages are being brought from the backing store to the physical memory. Now we will study if there are no free frames in the physical memory, then what algorithms we are using to bring a page from the backing store to the memory and clearing the memory with the pages that are already existing there. We have to send one page back to the backing store and to adjust the new one. So what should be the criteria for the page replacement? We will be discussing in this video now. Now, what is page replacement? Prevent over allocation of memory by modifying the page fault service routine to include page replacement. Use modify or dirty bit to reduce overhead of page transfers. Only modified pages are written to the disk. Right? Now we have discussed in the previous video that only those pages will be modified, those pages will be written or copied in the backing store if we are making some changes in that particular page. If the page is only used for reading purpose, then there is no need to update the page that is on the backing store. But if we have modified it, then we have to write it again on the backing store. For that, we are associating one dirty bit, or you can say a modified bit, with every page. If we are modifying it, then we will set that bit to modify. Means it is an indication to the OS that that particular page is being modified and we have to replace or we have to rewrite that page in the backing store. Page replacement completes the separation between the logical memory and physical memory. Large virtual memory can be provided on a smaller physical memory. Now, page replacements is a method that is used when the size of the virtual memory is larger than the physical memory, right? Now, see here, this is the scenario which tells why do we need a page replacement. Suppose the program counter is here and it is requiring the load M, right? This M is to be loaded here, and then this page table is updated with 4 is then to set to valid bit. After this instruction has to be accessed. That means you have to bring B from the backing store. Now, for this, the B is not there. See, it is only 6, 2 and 7 pages that are having frames that are having a valid bit. That means 6, 2 and 7, right? They are in the memory. Now, but it is desiring B. B is not there. So, B has to be brought from here to some place in the physical memory, right? But there is no space in the physical memory. Now, where to fit B? Where to set B now? So, for setting B, one of these pages has to be swapped out to swap in B here. So, this is the need for page replacement, so that we can fulfill the desire of this particular user 2, because at that particular time it is requiring B. If it not get B, it will be halted, it has to wait, and the CPU utilization will be less in that case. Now, what is basic page replacement? Find the location of the desired page on the disk, right? Whatever page is required, such we have to check where it is on the disk. Find a free frame, right? Now to bring that page from the backing store to the physical memory, there should be a free place for it. If there is a frame, then you can use it. If there is no free frame, then use the page replacement algorithm to select a victim frame. Now out of those pages, we have to select which page has to be sent back. So to choose that victim, we will be using different algorithms. Read the desired page into the frame which is newly created now, and update the page and frame tables, right? For the table which has been swapped out, you have to set the bit as I, and which page has been brought back into the physical memory, for that you have to set the bit V. Then after that, restart the program. Now, this is the definition which we was studying about page replacement. Let's understand with the help of a diagram. See, suppose this is the victim selected by the algorithm used. We will send back this victim here, right? Now this frame is free. This frame is free, right? For this, we will set these change to invalid. Now this particular frame, this V was in this memory, now V will be converted to I because this is free, right? Now, after that, this page will be brought here again, right? Now this page which was required, this set in that particular space. Again, this will be valid now because it is brought in this, right? And then reset the table for the new page and then restart the process. Now we will discuss various page replacement algorithms. The page replacement algorithms should be such that we have to reduce the number of page faults. Want the lowest page fault rate. Evaluate the algorithm by running it on a particular string of memory references and computing the number of page faults on that particular string. We will have different memory references, the string of different memory references, and we will be given how many number of frames are there in the memory. Then we will calculate how to adjust all these requests of pages with the limited number of frames. In our example, the reference string which we are using is this one. Means 1, 2, 3, 4, 1, 2, 5. These are the memory addresses which is being reduced to one digit so that you have a proper understanding of the algorithm and not get hodgepodge or get confused with long memory addresses. So that memory address is being reduced to compact 1 digit or 2 digit to make the concept clear, right? Now you see graph of page fault versus the number of frames. As we increase the number of frames, the page faults go on decreasing, right? See, for lesser number of frames, we have more page faults. As we are increasing the number of frames, the rate of page fault is decreasing because we have more space, and page faults are reducing, right? But sometimes there is a scenario that we are increasing the space, but we are also increasing the page faults. So let's consider this reference string. We are given with the first 3 frames, right? Now we have to see that 1, 2, 3, these are the 3 frames. Let's see how many page faults we get in traversing the whole string. Now, first, second, third, right? Now the algorithm followed in this is first in, first out. Means the page which has arrived first will move first, right? Now, see here, the first reference will go in the first frame, second reference will go in second, third will go in the third, right? Now, till here we have traversed. Now comes 4. 4 is want to go into the physical memory, but there is no page frame free. We have to replace one of it. So 1 has arrived first, so it will be replaced. So in place of 1, we will put 4, right? Then comes 1 again. Then now the latest one is second, we will replace it and put 1 in that. Then comes 2, we will replace 3 with 2 because 3 is oldest now. Till here we have traversed now, right? Now comes 5. 5 will be replacing 4 because 4 is oldest. Then 1 is, after that 5 we have 1. Then 1 will be replacing the 2, 1 is already there, sorry. 1 is already there in the memory. Then 2 is already there in the memory, right? Then 3 will be replaced, 3 will replace 1 because 1 is the oldest here, right? So 3 will come here. Then comes 4 will replace 2 because 2 is oldest now. Now last one is 5 will replace 4 because 4, this one has become the oldest now, right? Now what will happen, if we count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults, right? 9 page faults are there when we have 3 frames. Now we increase the number of frames. That means we are increasing the size of the memory. According to the logic, if we are increasing the size of the memory, the number of page faults should decrease. Now let's see. 1, 2, 3, 4, right? Again. Now see here. These are the 4 pages. First 1 will come here, then 2, 3, 4 and 4, right? All were free, that means they fit in the first lot only. Then comes 1 is there, already there, okay? Then comes 2, right? 2 will replace, 2 is already there, right? Then comes 5 will be replace 1 because 1 is oldest here, right? 5 will come here. Then comes 1, right? 1 will replace 2 because 2 is oldest now. 1 is there, we will fit 1. Then comes 2 will replace 3 because 3 is oldest, and 3 will replace 4 because 4 is oldest. Now comes 4 will replace 5 because 5 is oldest now. Then 5 will replace 1 because 1 is oldest now. Now let's count the number of page faults. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. See, with 3 frames we get 9 page faults, and with 4 frames we got 10 page faults. So this is a unsymmetric situation, you can say. And this type of situation is called Bilady's anomaly, right? This usually don't happen, but there are cases when we increase the size of the memory, the page fault increases. Now let's take the other example. See here, reference string is this 701 203 042 303 212 01 701, and we are having 3 page frames, right? With the FIFO algorithm, means first in first out, how we fit these pages into the frames. 7 here, 0 in next, 1 in here. Now these are over. Now 2 is to be set. 2 will replace 7 because 7 is the oldest. Similarly, now comes 0. 0 is already there here. 3 will be replaced. 3 will replace 0 because 0 is the oldest now, right? Again we come with 0. 0 will replace 1 because 1 is oldest. 4 will replace 2. 2 will replace 3. 3 will replace 0. 0 will replace 4. This way we will go because we have to check which is the oldest and we will go on replacing the oldest one. Now here 3 is there, no page fault, 2 is there, no page fault. Now we have to put 1. 1 we'll put here because 2 is the oldest. Then 2 will replace 3 because 3 is oldest now. 0 is already there. 1 is already there. Then 7 will replace 0 is oldest. Then 0 will be replaced by replacing 1 and 1 will be entered by replacing 2. Now out of the 3 we have to check which is the oldest and we will replace that. Now see how many page faults? 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 page faults in FIFO, right? Now optimal algorithm, replace the page that will not be used for the longest period of time. Means you have to go on checking this side that which is the farthest page number that will be replaced. Means the logic behind this, the page which is no longer used for a long time, that should be replaced because the program is not requiring that page for a longer time. So we can replace that page for the time being, right? Now let's see, we are having 4 page frames. So 1 will go in the first, 2 will go here, 3 will go here and 4 will go here, right? 1 already there, 2 already there, 5. Now 5 is to be inserted in this particular memory. Now this side we will see which is the farthest one. We have seen that the farthest one is 4, right? Then so we will replace 4 with 5, right? Then 1 already there, 2 already there, 3 already there, 4 is to be inserted. Now from this side we will see which is the farthest one. Now it is all the pages are finished, no requirement is there, so you will replace the oldest page, right? 4. Now how many page faults? 1, 2, 3, 4, 5 and 6. 6 page faults, right? How do you know this, that this particular page or will be not used in the future? Used for measuring how well your algorithms performed, right? Then you require a prior information by the program that I will be requiring these pages in future. Then only you can run this program on it. Now let's take the same reference string for optimal. See, 7 will go here, 0 will go here, 1 will go here. Now 2 has to be inserted. Now this side we will see from 701 which is farthest. 7 is coming here, 0 is coming here and 1 is coming here. That means 7 is the farthest. We will replace 7 by 2, right? Now 0 is already there, 3. Now we have to check 3. Where to insert 3? Out of 201 which is farthest? 2 is here, 0 is here and 1 is here. That means 1 is farthest. So we will replace 1 by 3, right? This way we will go on. 0 is already there. Now 4 has to be inserted out of 203 which is farthest. 0, 2 and 3, right? 3 is farthest, we will replace it by 0 we have already done. 4 is here, right? And then 0 is farthest, so we will replace 0 with 4, right? 2 is already there, 3 is already there, right? Now 0, we have to insert 0 now. 0, right? Out of 243 which is farthest? 2 is here, 3 is there, 4 is not there anywhere, so we will replace 4. 4 will be replaced by 0. 3 is there, 2 is there, 1. Now 1 has to be inserted. Out of 203, which is farthest, 2 is here, 0 is here, 3 is not there, so we will replace 3. Right? 2 is here, 0 is here, 1 is here, 7 is to be inserted. 201, which is farthest, 0 is here, 1 is here, 2 is not there, so we will replace 2 and we will insert 7 in that place. This way it goes. Now, least recently used algorithm, right? Least recently used algorithm means the page which is not used for a longer time in the past, not used for a longer time can be replaced. So the logic behind this is, if we can say that it is not being used for a longer time, that means it is not required for the time being, right? So we can replace it. So it is the reverse of the optimal. In optimal, we were saying to the right side where the pages were farthest. But now in least recently used, we will see this side, okay, which is the longest away that page will be replaced. Now see here, 701, right? Now 2 has to be inserted this way, which is the farthest among 701. 7 is the farthest, so 7 will be replaced by 2. 0 is here. Now 3 has to be inserted. Out of 201, which is farthest, 0 is here, 2 is here and 1 is here. So 1 is farthest, so 1 will be replaced by 3, right? 0 is already there, okay. Now 4 has to be inserted. Out of 203, which is farthest, 0, 3, 2. 2 is farthest, so it will be replaced by 4, right? 2, 403, which is the farthest, 403. 3 is farthest, then 3 is replaced by 2, right? Now 3 has to be inserted. Out of 402, which is farthest, 0. 0 will be replaced by 3, right? Now, again 0 has to be inserted. 432, which is the farthest, 4. 4 will be replaced by 0, right? Now, 3 is already there. 2 is already there. 1. Out of these 3, which is the farthest, 0 is here, 3 is here, 2 is here, so 0 is farthest. So, replace 0 with 1, right? 2 already there, 0. Out of these 3, which is farthest, 1 is here, 2 is here, 3 is here. 3 is the farthest, so replace 3 with 0, right? 1 is already there. 7 is to be inserted. 102, which is farthest, 2. 2 replace 2 with 7, right? 0 already there, 1 already there. So this way you have to perform least recently used page replacement algorithms. You can count the page faults: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 page faults. Now you can see here, with optimal we got 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults. See, right? Now see here. With C4 we got 15 page faults with the same string, right? With optimal we got 9, and with least recently we got 12. So in this scenario, the optimal page replacement is the best algorithm because the minimum number of page faults in that case. Now the least recently used approximation algorithms, reference bit. With each page associate a bit initially 0. Now what you have to do, we have little extension to that particular algorithm. First we will associate one bit, reference bit, to every page, right? When the page is referenced, the bit is set to 1. If we are referring that page, we require that page, we will change the bit. Replace the one which is 0. We do not know the order, however. Now we will not check which is the latest, which is the longest, which is not recently used. We will just check the bit. If we get the bit number 0, then we will replace it when we can use it. This means that we are giving a second chance to it, right? Need a reference bit, you need a clock replacement, right? Now we are not to take care about the clock which is being telling us that how long this process is being used. If the page is to be replaced as reference bit 1, then we will set a bit to 0. That means we are giving that particular page a second chance. Why do we doing this? We are doing this because according to the theory, we says that if a program is being referenced just now, right, that means 1, if the reference bit is 1, that means it's recently referred, program has recently referred this particular page, right? That means least recently used says that those who are just referred can be used again. So that's why we are giving a second chance to that particular page, right? So first we will check whether it is 1 or 0. If it is 1, we will set to 0 and leave that page. We will not replace it, right? Then we will come again to that page after referring the other pages. If we get the reference piece again 0, then we will replace it, right? Leave the page in that memory after setting the bit, replace the next page subject to same rules. Means here we are not to take care about the clock. Now let's understand this with the help of an example. See, these are the pages. These are the reference bits associated with it, 0, 0, 1, 1 and so on, right? Now let's suppose we are to replace one page. We want some page. So according to the algorithm, this is the first victim selected because this is having the bit 0, this is having the bit 0, this is having the bit 1. So this should be replaced. But we will not replace it, we will set it to 0 and go to the next, right? Again we see there that it is 1. We will set it to 0 and go it to the next, right? Then this we are getting 0, this will be selected as a victim. This is selected as a victim. And these will be set to 0, means they are given a second chance, maybe you can be referred again, right? Counting algorithms. Keep a counter of a number of references that have been made to each page, right? First is least frequently used. In previous, we did least recently used, right? Here the algorithm is least frequently used. Here we will associate a count. Number of time the page is being referred, we are increasing the count of it, right? Then the least frequently used page means with the minimum count, the page will be replaced. That means that page is not required frequently, so we can replace that page. Most frequently used algorithm, based on the argument that the page with the smallest count was probably just brought in and has to be get used. Here, if the logic behind most frequently used is, we can say that this particular page has been used a number of times and the other one is used lesser number of times. So maybe that programs require the lesser number of the page which is having lesser number of counts. Because it is not being used, it is in the memory, that means the program will require that particular page more than the most frequently used. What is thrashing now? If a process does not have enough pages, the page fault rate is very high. This leads to low CPU utilization. Operating system thinks that it needs to increase the degree of multiprogramming, and other processes are added to the system. Suppose our virtual memory, or you can say is very large and the physical memory is very small to that compared to that virtual memory. Then what will happen? When the pages are required by the program, the physical memory is small, so we have to bring the page from the backing store again and again. We have to replace the pages. So there will be the number of page faults will increase in this case. So that time the CPU is sitting idle, right? The OS will think that OS CPU is idle, that means we can increase the multi-programming level. So it will take more and more programs, but ultimately the programs are not running by the CPU, but they are busy in the page fault, right? Such a situation is called thrashing, where the program is busy with the page fault rather than using the CPU for its execution, right? So this type process is called thrashing. A process is busy swapping pages in and out, right? See the situation. CPU utilization with degree of multi-programming first increases to some level. But when there are page faults occur, then it suddenly comes down and the degree of multi-programming go on increasing, but CPU utilizations come down. When there is a sudden downfall, this method is called, or this situation is called thrashing, right? Why does paging work on the locality model? Now, paging will be more understood if you are aware of what is a locality model. Process migrates from one locality to another. Localities may overlap to each other, right? Why does thrashing occurs? Size of the locality is greater than the total memory size. Locality means at a particular time, the number of pages it is requiring is called the locality. Suppose a program is using 5 pages. At particular time, it is requiring 1, 2, 3 pages. 4 and 5 it is not required. So now this program will have 2 localities. First locality will have 1, 2, 3 pages, and then second locality will have 4 and 5 page numbers, right? At a particular moment, that is the locality, right? And if that locality is larger than, suppose we are in a locality at a particular time, a program is requiring 10 pages and our physical memory is having only 5 pages, then there will be more page faults. Now see what is happening here. What is a working set model? This symbol is saying that it is called a working set window and a fixed number of page references, for example 10,000 instructions. Working set process PI, total number of pages referenced in most recent delta, right? If delta is too small, will not encompass entire locality, and if it is too large, it will have several localities at a time, and if it is infinite, it will encompass the entire program. Now, D is total of all the localities it is using of all the timings, right? That means total demand frames, it will require the frames, total number of frames it will require at a particular time. If D is greater than the memory, then it will lead to thrashing, right? And if is policy, if D is greater than M, then suspend one or more processes. What is the solution to thrashing? You can suspend one or more processes for a time and then you can run these other processes quickly. Now see, these are the references strings of a program. If we check at T1 time, at a particular time, right? This is the working set model or delta. So this particular time, which all pages are required? 1 is required, 2 is required, 5, 6 and 7 is required. So this is the locality, right? Similarly, at this particular time, and this is the delta, then 3 and 4 is required in this. See, other than 3 and 4, there is no other page number. So this is the locality. Other considerations, TLB reach, the amount of time memory accessible from TLB. TLB reach is equal to TLB size and into page size. In our third video, we studied about TLB. It was translation look aside buffer, right? It was the time required to access that buffer, that is the TLB time, right? Ideally, the working set of each process is stored in the TLB. Because TLB is a translation leukocyte buffer, it is faster than memory. We can keep a particular program or locality of that at that moment, whatever pages are required, we can keep in TLB so that the execution is faster. Otherwise, there is a high degree of page faults, right? Now, there is another solution. If we can increase the size of TLB, then increase the page size. This may lead to increase in fragmentation, and not all applications require a larger page size. Now, if we are increasing the page size, then can lead to fragmentation, right? And if there is fragmentation, then maybe we are going at loss. So that means all the programs do not require large spaces. So we should keep the size of the page mediocre only. Provide multiple page sizes. This allows applications that require larger page size the opportunity to use them without an increase in fragmentation. You can have an option of multiple page sizes also. Some are larger and some are bigger according to the requirement. The programs can use that pages. Thank you very much.